Welcome to U7L3 compound probability. Okay, so in this lesson, we're going to talk about the probability of two or more events happening. So the events can either be independent or dependent. All right, so events are independent events if the outcome of one does not affect the likelihood of the other event occurring. An example of this is rolling a die, then flipping a coin. They're two separate items. They have no effect on one another. So those are independent events. So when A and B are independent of one another, okay, independent, the probability of A intersected with B, so the probability that they both happen, okay, that's what that means. The probability that they both happen is just going to be the probability of A times the probability of B. Okay, and that's all that is. You just multiply the two probabilities together. So here's some examples. If the spinner, to the right is spun, then a letter from the word unicorn is chosen at random. Find each probability. So this spinner is going to be spun, and then we're going to choose randomly a letter from the word unicorn. So let's look at the totals first, and then we'll do these probabilities. So first of all, the total of the spinner is 1 through 10. So the total over here is 10. The total for the word unicorn, so there's 1, 2, 3, 4, 5, 6, 7 letters. So the total there is 7. Okay. Doesn't matter that there's two N's. The total is still 7 because each letter counts. Okay. And these are independent because the spinner and the word unicorn have nothing in common. They're not related. They don't affect one another, okay? All right, so probability that you get less than 7, then a C. So probability of less than 7, let's take a look. Less than 7 is going to be 6, 5, 4, 3, 2, 1. So that's going to be 1, 2, 3, 4, 5, 6 numbers. So that's going to be 6 out of the 10 total. Okay, and then we're going to multiply that by the probability of getting a C. Well, there's only one C in the word unicorn, okay? So that's 1 out of 7. So times 1 out of 7, okay? You can go ahead and simplify first if you want. So you can change that to 3/5 times 1 over 7. And you're going to get 3 times 1, which is 3, over 5 times 7, which is 35. And then change that to a decimal. So 3 divided by 35. Going to give us 0.0857, or if you move your decimal 2 places to the right, that's about 8.57%. So not a very high chance that you're going to do that compound event, that's going to happen, right? Okay, next one, probability of an even, then n. Okay, so even. So even should be half these numbers, right? 2, 4, 6, 8, 10. Everything divisible by 2. So that's 5 of them. So that's going to be 5 out of the 10. Or we can change that to a half. So 5 out of 10 times getting the letter n. So that's 1, 2. So there's 2 out of 7. So times 2 out of 7. Again, I'm going to change it to 1/2 times 2 out of 7. Oh, I noticed something that's going to make my life easy. So I'm multiplying by a 2 and I'm dividing by a 2. Right? That's what it means when I have something, the same number in a numerator and denominator. I'm multiplying and dividing by the same thing, which just equals 1. So I can actually get rid of that. And then it'll just be 1 over 7. It'll be what's left. Okay, 1 over 7. So 1 divided by 7 is then going to give me 0.1429 if I round. 1429. And then we're, of course, going to round, or not round, change it to a percent. So that's about equal to 14.29%. A little bit more likely than the last one. All right, last one here. So it says probability of an odd, then a vowel. So odd. So odd is going to be 5 out of 10 again. Odd is everything that's not divisible by 2. So 1, 3, 5, 7, 9. 5 of them. Actually, I'm just going to go ahead and put 1/2. Well, no, I don't want to confuse you. Okay, 5 out of 10 times a vowel. Vowels are A, E, I, O, U. So A, E, I, O, U. So U, I, O. So there's 3 of them out of 7. 3 of them out of 7. Again, changing that to 1/2 times 3/7, multiplying numerator to numerator, denominator to denominator. So 1 times 3 is 3, 2 times 7 is 14. If I do 3 divided by 14, I get 0.2143 if I round, and that's about 21.43%. About a 21.43% chance of getting an odd number on the spinner and then choosing a vowel from the word unicorn. All right, two more. Example 2. A month of the year and a day of the week are chosen at random. What is the probability of choosing a month starting with J, then Monday? Okay, month of the year and a day of the week are chosen. So let's look at our totals first. So month of the year. So there are 12 months in the year. So there's 12 total. Okay, for this part. And then days of the week, there's 7. So there's 7 total. Okay, so we have 12 total months in the year, 7 total days of the week. So those are our totals. And it says, what's the probability of choosing a month that starts with J? That's our desired there. And then Monday, which is our other desired outcome. These are definitely independent, right? They have nothing to do with one another. If you're just picking them at random, they're not going to affect one another. So we have the months out of 12, a month starting with J. So January, and then February, March, April, May. So June. So January, June, July, August, September, October, November, December. So 3 of them. So 3 out of 12 times Monday. That's only one day of the week, right? 1 out of 7. Simplify 3/12 to 1/4 times 1/7. And then multiply numerator to numerator, denominator to denominator. 1 times 1 is 1. 4 times 7 is 28. This is not looking very likely. 1 divided by 28 is equal to 0.0357, or about, if I change this to a percent, it's about 3.57%. Not very likely in this scenario. All right, last independent event here. Jackie guessed on 3 problems on her multiple choice test, each having 4 options. What is the probability that she got all 3 questions correct? So Jackie guessed on 3 problems. It's a multiple choice test with 4 options each. Now we need to figure out the probability that she got all 3 questions correct. So basically we have to look at this as 3 separate events compounded together, right? So here's how I want to look at it. So here's the first question that she answered, the second one, and the third one that she guessed on, I guess I should say. She answered more, but these are the ones she guessed on, okay? If there's 4 options, only one of them is correct, understanding how multiple choice works, right? Then the first time that she answers it, there's 1 correct out of the 4. So that's the probability of getting it correct. But then that's the same the second time as well, right? 1/4, and same the third time as well. But the thing that we have to do here, let me give myself a little more space to do this. The thing that we have to do here is it's a compound event. We want to know the probability that she got all 3 of them correct, that she got all 3 questions correct. So we need to multiply those together, okay? So the probability that she got all 3 correct is 1/4 times 1/4 times 1/4, okay? Which is going to be 1/64. So if you change that to a decimal, it is 0.0156, or a little bit more, about 1.5% really, right? Which is equal to 1.56%. Not likely if you have a multiple choice test and you guess, right, completely guess on 3 problems, that you're going to get all 3 of them correct. Not very likely at all. All right, now let's look at dependent events. So events are dependent if the outcome of one event does affect the likelihood of the other event occurring. An example of this is choosing a marble from a bag, not putting it back, then choosing another marble from the same bag. What happens there is the total changes. So one main way that you know you have dependent events is if the total has changed, is if you have some situation where you have a marble or some other item and it's not being put back in the same location, right? So now you cannot choose from it. Or if you're talking about choosing a student or a runner in a race, and you're talking about choosing more than one. Well, once you choose the first runner, that runner is chosen, right? They're no longer in the pool of people to be chosen from. So the total has changed. Things like that. Those are going to be dependent events, okay? Okay, so when A and B are dependent, meaning that the outcome of one is dependent on the other. Then the probability of A intersected with B, so the probability that they both happen, that's what this still means, okay, that's what that intersection means, is now going to be the probability of A times the probability of B after A. Meaning that you have to keep in mind that the probability of B happening after A is going to change something, right? That something is going to change versus the probability of B happening just on its own, okay? So usually it's the total is going to change. All right, let's take a look at this. For example 4, a bag contains 3 blue marbles, 10 green marbles, 4 yellow marbles, and 8 red marbles. A marble is chosen at random, not replaced, then another marble is chosen. Find each probability. So when one marble is chosen, okay, whatever color it is put to the side. It is not put back into that bag. Okay, so it's not replaced. So the total changes. Which means that this has to be a dependent event. So first things first, let's figure out the total at the beginning. So we have 3 plus 10 plus 4 plus 8. Add those all up. I'm going to do it in the calculator just to make sure. 17 plus 8 should be 25. Okay, so the total is going to change, but the total is starting with 25. So we have 25 total to begin with. Okay, so now we're going to do these probabilities. So the probability of red, then blue. So the probability of red is the first one. That's based on the 25 total. So we have 25 total marbles. The probability of getting a red is going to be the 8, right? There's 8 red marbles. Times, still the probability, right? But now that red marble is to the side. So now there's only 24 marbles. I'm going to say 1 red is missing, right? And so that's why in this case, right, that total's changing and this is dependent. And now we're going to get a blue. So how many blues are in there? Well, there's still 3 blues. Nobody touched a blue, right? So there's 3 blues. Okay. Let me move this down a little so I can finish the math. There we go. Multiply 8 times 3, so 24. The numbers get kind of crazy. So 8 times 3 and then 25 times 24. We actually could have simplified that first. I'm going to point it out how to do it. You could have simplified 3 over 24, or you could have simplified 8 over 24. This would have been a 1 and this would have been a 3. So we could have done that first. 24 over 600. So to simplify that, 24 over 600 is going to be 1 over 25, which as a decimal, 1 divided by 25 is 0.04. 0.04. So about 4%. About 4% of a chance getting a red and then a blue. Not very likely. All right, let's look at this next one. I need to separate those. There we go. Yeah, that's fine. Okay, it says probability of a green, then a yellow. So again, we're taking the green one out. And then we are going to consider the yellow once the green one is missing. So probability of a green one. So there's 25 to begin with. Probability of getting a green one, well, there's 10 green, so 10 out of 25. Times the probability of then getting a yellow, where now there's only 24 marbles because one of the yellows is missing. Or one of the greens is missing, excuse me. And then there's 4 yellow marbles still in there. Let's go ahead and simplify these to make it easier. So 10 over 25 is equal to 2 over 5 times 4 over 24, which is 1 over 6. So that's equal to 2 times 1, which is 2, over 5 times 6, which is 30, which is equal to 1 over 15. So let me do that as a decimal. 1 divided by 15 is 0.0667, or as a percent is 6.67% likelihood. Okay, let's keep looking. So for the probability that they are both red. Okay, so the first time you have 25 marbles, and 8 of them are red. So that's 8 out of 25. But now one of the red ones is to the side. Oh, sorry. One of the red ones is to the side. Okay, so now there's only 7 red. So now there's only 7 red left. Okay, and there's only 24 total. So the total has changed to 24, and now there's only 7 red left. So that changes both the numerator and the denominator this time, so be very careful. Now I can simplify this. I'm going to go ahead and show you how to do that. 8 and 24 have an 8 in common. So I'm going to change that. I'm going to divide the 8 on top and bottom. That's going to change that to a 1 on top and a 3 on bottom. And now I'm going to multiply those numbers. So 1 times 7 is going to be 7, and 25 times 3 is going to be 75. Divide that. 7 divided by 75 is going to give me 0.0933, or 9.33% chance of getting both reds. Last but not least, let's take a look. Probability of not blue, then blue. So the probability of not blue, first of all, there's 25 marbles right now. We've just started. The probability of not a blue one is everything except for those 3 blues. So that means it's 25 minus 3. So it's going to be 22. So there's a high likelihood that the first one's not blue. That's a high likelihood. Times the probability of then having a blue. Well, we didn't get a blue to begin with, so there's still 3 blues in there. Okay, so it's 3 over, and then the total has changed to 24 because whatever color we did get, we took it out. We took it out. Okay, I can simplify this a little bit if I want to. I can simplify, let's see. 22 and 24 have a 2 in common, so that's 11 and 12. And then 3 and 12 have something in common. They have a 3, so that's 1, and that's 4. If you don't want to simplify like this ahead of time, you don't have to. You can just multiply numerator 22 times 3, and then 25 times 24, and simplify later in the calculator, or however you want to do it, okay? I'm just doing this to make it a little bit neater. All right, so that means I'm going to have 11 times 1, which is 11, over 25 times 4, which is 100. So 11 divided by 100. 11, sorry, I'm trying to use the calculator, is about, oh, duh, it's 11%. Okay, I just did the calculator. It's 11%. I'm just making sure I didn't mess something up. Yeah, okay. So that's about 11% chance. All right, let's look at example 5 now. A class of 32 seniors were asked if they are going to college after graduation and if they have a job. Of those surveyed, 21 said they are going to college, 19 said they have a job, and 8 said that both options apply to them. If 2 students are chosen at random, find each probability. Okay, so in this case, this is dependent again, and that's because once you choose a student, right, they're kind of put to the side. You've already chosen that student, so that student cannot be counted in the total after that. Now, whenever we get a scenario like this, I always recommend we do a Venn diagram. Okay, so let me do a Venn diagram real quick of the situation. So we have 2 situations. Going to college, C for college, so I'll put a C for that. And then if they have a job, I'll put a J for that. Okay, so J for job right here. Let me, hold on. I don't want this to be neat for when you guys have these notes to look at, so let me fix this real quick. All right, and then all right, and it says there was 32 seniors, so that's the grand total. So that's how many need to be in our box, right, in total. We always start with the intersection. So it says that there's 8 that there's 8 people that said both options apply to them. So there's 8 in the intersection. Let's see, it says that there's going to be 21 said they're going to college. So 21 college, so 21 minus 8. 21 minus 8 to see what's left is 13 in the rest of the college circle. And then for jobs, 19 said. So 19 minus 8 is going to leave us with 11. Okay, and if we add those up, 11 plus 8 plus 13, we get 32. Okay, so that means that there's 0 out here because we get, that's, all of them are accounted for, right? Every single person said they either have a job or are going to college or both, okay, or both. So there's 0 on the outside of that. Perfect. Okay, so both students, what are the probabilities? Both students are going to college but do not currently have a job. So both students are going to college but do not currently have a job. So the first time we pick a student, there's 32 total. And it's saying that they're both going to college, but they do not currently have a job. So that means that they can't be in the intersection. They have to be in the 13. Okay, so the first time I pick one, there's 13 to choose from out of 32. But then the next time now one of the students is already counted for. So that's only 31 students. And since these students came from the same section of my Venn diagram, that total has changed to 12. Okay, so since it's the same group of students, okay, the total changes and the desired outcome changes. Okay, and that's because we're talking about the students coming from the same group of students, right? The same section of our Venn diagram. All right, so let's go ahead and simplify that. I can simplify a little ahead of time if I want to, but I'm just going to go ahead and just go straight for it. 13 times 12 is 156, and then 32 times 31 is 992. We can simplify this. If you use the alpha button and the one next to it, it'll be faster. That's going to be 39 out of 248. Definitely want to look at that as a decimal. So 39 divided by 248 gives me 0.1573, or about 15.73% chance that both of those students are going to be going to college but don't have a job. So not a high likelihood there. Last but not least, it says one student currently has a job and the other neither has a job nor is going to college. So the first student has a job. Okay, has a job. So all the students that have a job are going to be at the 11 plus 8, which is 19. So we're choosing from 19 students out of the 32 total. Times. Then one of the students is accounted for, so the total definitely goes down to 31. This next student, though, neither has a job nor is going to college. So this one's actually kind of funny. So the students who neither have a job nor are going to college was 0. So that's actually 0 out of 31. So no matter what, this whole thing is going to multiply to 0. And there's a 0% chance of that happening. Because as I pointed out in the beginning, every single student was accounted for with either going to college or having a job. Okay? So for this one, it's actually a 0% likelihood that can happen. Okay. That's it for these notes. Thanks for watching. Have a great day.